In the last video, we've just been looking at trying to estimate the surface temperature of an exoplanet in a better way. So we started by assuming that the star's light was actually emitted in all directions, and of course, then we have only some of it that actually reaches this distance where the planet is. But of that, of course, we have some of it only reaching the planet itself. So because the planet only has one side that's dark, one side that's light, because of that, and we take into account the albedo, we have that the absorbed light, or the absorbed power, is going to be given by this equation here. That was sort of step C, I guess you could say. Now let's take this step C and just take it one little step further here. So on the next page, I'm going to do that. So we're still on part C. What we're going to do then is just take a look at these right here, just to simplify things for us. If we go down, we have something pi r squared and something with 4 pi d squared. So that means we can just cancel out the pi's. That's all we're going to do here. So we have that the absorbed power then, L absorbed, is just going to be the same equation except we canceled out the pi's. So we have the luminosity of the star times the radius of the planet squared divided by 4 pi, oops, not pi, just got rid of it, 4 times the orbital distance squared, all that times 1 minus a. That was the absorbed light. But we have step D. And what this is that, well, we need to know the radiated. So what does the planet actually radiate outwards? So that's going to be important too. So we have L rad. And that's going to be because L rad is going to be equal to the power radiated away by the planet. Okay, that's going to be what's this L rad. And of course, that's going to be measured in watts. Well, what we're going to do there, we're going to use Stefan Boltzmann. So this, it is accurate, I think, and it is relevant to use this. So 4 pi r squared times sigma times t to the power of 4. That's going to be the equation governing radiated light. So in other words, now we're looking at this planet right here. So this is, let's say, the planet here. And we're basically looking at, what type of light is absorbed, that's L absorbed here, compared to what's radiated away, L rad. And we're going to assume then that everything that's absorbed is radiated. And the reason is, that's because we're assuming that the planet was a black body. Okay, so E. Because the planet, this is the key thing here now, because the planet is a black body, which we've seen in previous videos, that tells us that what is radiated away is the same as absorbed. We can then say that L absorbed equals L rad. Now, it was a little bit complicated to see what was absorbed in the planet, but now this is a simple idea here now. So because it's a black body, just set these two equal to each other, and that's it. So that means then that we can just set them equal to each other, and away we go. So what's L rad? Or maybe I'll write the L rad first. So I'll do that one first. So that means I get 4 pi r squared sigma t to the 4th equals L star times r squared over 4d squared times 1 minus a. And we can take a look if anything cancels out, and thankfully there is. Take a look at this r squared here and this r squared. Those can cancel out. That's because I can divide both sides of the equation by r squared, and that would make this a 1, and that would make this one a 1, so it would disappear. That made things a little bit easier. So finally, the very last step then, now we calculate. We calculate the surface temperature of the exoplanet. So how do we do that? Well, we just calculate for t to the 4th here. So we just get t 4th by itself here, t to the 4th. It's going to be equal to, well, I just have to get rid of the 4 and the pi and the sigma and put them on the bottom here. So on the top, I have an L star, I have a 1 here, and I have a 1 minus a. That's the only things on the numerator. On the denominator, however, I have this 4 pi d squared initially, but I also have a 4 pi sigma. So it was just 4d squared here, but here it's a 4 pi sigma. And the reason is that this pi here came from a different one. See, before we canceled out the pi's, but that was from the absorbed one. There was no pi's. But the L radiation, that one, the radiated power, that one has a pi sitting there. So because of that, then we have this. And then just to pretty it up, then we'll say that t to the fourth is going to be equal to, well, L star times 1 minus A, all that over, let's see, 4 times 4, we can make that a 16. And what we normally do is write the pi and the sigma next. And then after that, we'll just do the d squared. So this is a much better way to estimate the surface temperature of an exoplanet. So this may have seemed really complicated to get to at first, especially with this absorbed power equation. But this one here is going to be a very, very useful way to do it. And it's much better than the very crude method that we had used before. So again, just to remind you then, so the T, that's the surface temperature of the planet. I like to write this just beside an equation here so we can see everything. And that's going to be in Kelvin. Well, L star, that's the emitted power of the star. And that's in watts. We have A, that is the albedo of the planet. And remember, that takes into account either atmosphere or the color of the planet, or maybe the combination of both. That has no units. And of course d, because pi is a constant and sigma is a constant, and d, that's the orbital radius of the planet. So all you need to know is these things right here, and you can estimate the surface temperature. Now, of course, you'd have to, this is t to the power 4 is all this. So once you calculate this, you'd have to take the fourth root of this, or take this whole thing and bring it to the power 1 over 4. But, I mean, that's doable, I think. So what we can do then is take a look and, well, we can use this. But now the problem is, for exoplanets, though, we do have to make a lot of assumptions. And one of them, for example, is, well, I mean, we have made a lot of assumptions here. So we made a lot of assumptions. Okay, and those assumptions were lots of things. I mean, we assumed, for example, that, well, we assumed a planet is a black body. We assumed circular orbits. We didn't really do much with the atmospheres. And we used basically only basic physics, so we really didn't go that detailed into it. But just with these sort of assumptions, we can still do a lot of things. And so it might be actually kind of interesting to see how close we can get to accepted values. Now, with exoplanets, it's hard to sort of know what to use for albedo. I mean, what do we use for the value of albedo for an exoplanet? I mean, this is something that I don't think is that sort of simple. But what we can do, I mean, we can actually use estimates of albedo. And what we do then is we usually use a value of, let's say, 0.3. That's actually the most commonly used thing. So a lot of the times they use albedo is around 0.3. Now that's just, they're guessing, of course, because it all depends on the color of it, and it's very difficult to do that with exoplanets because we don't really take direct pictures of them. But just to test the use of this equation, because if we did know the albedo of the exoplanet, then we can actually calculate its surface temperature. And it turns out with exoplanets, they can do something with albedo, or at least know something about the atmosphere. And that's because if you use the radial velocity method, let's say first, to detect something, and then use the transit method, it turns out from that you might be able to take a spectrum of its atmosphere, in a sense. So from there you might have some guess at the albedo. And because of that, then this equation here becomes very interesting. So as we get better and better results for exoplanets, this equation for the surface temperature of this planet is going to be much more important, because then we can sort of zero in on what this albedo value will be. But just to sort of test that, although we used a lot of simple assumptions, I thought it'd be fun to sort of test this equation out with sort of some accepted values.